Hey class, welcome back to Bayesian Stats. As you can probably tell, I'm not in our typical classroom with our class. There were some technical difficulties on Monday's video, so I'm back here to record it for you guys so you have the material. Also, I'll be uploading the notes at the end of the week, like every other week. Today we're going to be discussing Jeffrey's priors. We're going to be trying to motivate why they're beneficial to us, why we want to use them, as well as showing you guys what the Jeffrey's prior is and some examples to really understand and actually see where some of our priors have come from. Before we do that, I want to quickly discuss homework 3. So homework 3, there are two problems that deal with Wishart. So if we scroll down to problem 4, we can see we have a Wishart distribution here. And we're going to try and find the full conditional of sigma inverse or the precision. And right now, we don't know what the Wishart distribution is. And at the end of next class and Friday, Dr. Lehman's going to be talking to us about the Wishart and inverse Wishart distributions. So for problem 4, only the full conditional on sigma inverse or the precision. You can save that until the next homework. Also, problem 6 will deal with the Wishart, and again, you can hold off on those problems, problem 6 and that subpart of problem 4 until next homework. The rest of it's due Friday. With the logistics out of the way, let's get started on understanding and learning about Jeffrey's priors. Now, Jeffrey's priors should, I'll wait until that goes up. Cool. Didn't know how the sound would act on camera. So Jeffrey's priors, to understand where in the motivation, we have to understand who Sir Harold Jeffreys was and what his profession was. And so right now, since you're at home, I would ask you to wiki what his profession was. And you're going to find that he was a physicist. And if we want to be specific, he was a geophysicist, he was an astronaut, he was a mathematician, he was a statistician, and during those times, he was probably a philosopher too. And what Jeffreys was really working on was all about our solar system. And a fun fact, which I think is cool, is he was also one of the guys that helped us to discover that the core of the Earth was molten or liquefied. I think that's pretty cool. How does that relate to Jeffrey's priors? Well, he's doing a lot of these inferences on parameters. And he doesn't want one person's arbitrary choice of a parameter to inflict and be different than if someone else is using. So what do I mean by that? Let me clear this up. So let's say, so he was a physicist, and his whole idea was, regardless of the parameterization you use, we should hopefully still come up with the same inferences on our various parameters. So let's say we have our xi's, save that, coming from a normal, mu, sigma squared, I equals 1 to n. We know the likelihood. For this case, we are going to say sigma squared is known. We're just trying to keep it simple, trying to understand where we're going. Okay? We know the likelihood, mu, conditioned on all of our data, and sigma squared is going to be proportional to e 1/2 x bar minus mu squared over sigma squared n. This is also proportional to, and you can verify it on your own, it's proportional to the product, I equals, I is going from 1 to n, e to the minus 1/2 xi minus mu squared sigma. Try to get more ink in this pen so I don't run out too soon. Okay? Now, a question that I posed in class is question, what prior should we use on mu, i.e. p mu equal to what? And I had one of our students, I believe it was Muhammad, give us an option of proportional to flat. And this is a good option. And then I proposed, do we have any other options? And some other options that students could have came up with is they could have said a normal, conjugate normal, right? So we could have said maybe a normal, because we know conjugacy, mu star sigma squared star. And the question I would have posed to them is, how are we going to pick mu star and sigma squared star? We don't really know much about the data, we're just saying we know it follows a normal. How would you pick these? And so I'd want you to think about that. How would you pick those? One good option is by blowing out the variance, but as you blow out the variance, it would come back to this flat prior. Additionally, we also have a lot of good reasoning on why we've been using this in the past class. A little foreshadowing, but we've seen this before, we're comfortable with it. Hopefully you guys all agree that this is a good prior for our problem. Now here's the question. If I had someone come in right now, can't because of COVID, and they said, I want to do a different color. They don't like this parameterization. What they like is xi follows a normal where our mu is 1 over psi, and then our variance is still known. Let's see if I get it. This is still known. And we still have data. Okay? And so we have someone that comes in and they like the inverse of the norm, or the inverse of the mean. They like being different. Sometimes this is hard to think about, so it's typically why we use just mu. But let's say they did. They have good scientific reasoning on why they want to use this. My question, before we get that, let's look at the likelihood. It's always good to look at the likelihood. So the likelihood of psi, given our data and our variance, again known, will be proportional to e 1/2 x bar minus 1 over sigma squared divided by n. Okay? So this is our likelihood. And the question, as we're Bayesians in this class, is what prior do we use? So let's think about that. Question. What prior do we use on, try to find the eraser, V. Boom. What prior? Now, in class, again, we had someone say, let's do the flat prior. This seems reasonable. Let's say the prior to phi is the flat prior again, or constant to 1. And I have a lot of people agree with this. A majority of the class, I would say 11 out of 14 students, agreed. Seems like a reasonable option, okay? But then I had someone also propose proportional to 1 over psi squared. Okay? And again, I polled, just so you guys know, and the majority of the students liked pi psi proportional to 1. And only a couple liked 1 over psi squared. If you're sitting in your room and you like this one, make a mental note to yourself. Because hopefully you also agreed we liked pi mu is proportional to 1. Here's the thing though, if you like pi mu proportional to 1, you should absolutely like the prior for psi to be 1 over psi squared. Why? Because it's going to go through a simple transformation. So if we have, if you like pi mu proportional to 1, you should like pi psi proportional to 1 over psi squared. Why? It's transformations. So if we were looking at pi, doing the quick transformation, will be equal, so our pi, do a quick transformation, mu our prior on mu, which will be 1, and then we go 1 over psi, taking the derivative with respect to psi. This will be equal to 1, because again, 1. Now taking the derivative of 1 over psi is 1 over psi squared. So just through simple math laws, if you like the flat prior on mu, then you should like 1 over psi squared. If you like this flat prior and you like this flat prior, you're being inconsistent. And that is what we're about to go look at, is why if we do an overall flat prior, are we being inconsistent? So let's look at this. No one's in the room, that's why my mask's off for any Virginia Tech people watching that are higher up. So what we were looking at is really two options. We can have the prior on both parameters just be flat, and we're going to make that a rule. We're going to make this rule. We have this rule. Which we're going to call the non-invariant to transform rule. Whenever someone says non-invariant, always ask to what? In our case, it's to transforms. Okay? So our rule is for any parameter our prior is flat or uniform prior. Okay? That's going to be our rule. I'm going to foreshadow. You do not want to use this rule, and let's see why. So we have two experimenters. We had one experimenter who liked, so experimenter 1 was our typical person who said they like their data coming from a normal with mu sigma squared. Again, we have our data. And their prior, our likelihood for mu is proportional to E 1/2 x bar minus mu squared divided by sigma squared n. And our prior, because this is the rule we're going to use, is saying mu is proportional to 1. Based off right here, we can make our posterior. Our posterior for mu is likelihood times prior, so we get x bar mu squared. Okay? Simple. We've done this before in this class. Now here's the interesting part. Let's say our experimenter 2 comes in. And they're going to use their parameterization, which is 1 over psi. Let's just write this out one more time. Make sure we understand. They're saying their mu is 1 over psi, sigma squared. Again, we have all of our data. Our likelihood for mu, not for mu, for psi, xi, is proportional to E 1/2 x bar minus 1 over psi squared, sigma squared over n. Now, what's our prior? We are going to use our non-invariant to transforms rule. So our prior will be pi psi proportional to 1. Okay? From here, we're going to calculate our posterior again for psi. Our posterior for psi, sigma squared, is proportional to E 1/2 x bar 1 over psi squared sigma squared divided by n. Okay? So now what we're going to do, right now, experimenter 2 is talking about a distribution on psi, and experimenter 1 is talking about a distribution on mu. But what if they want to talk about the distribution or probability space on the same parameter? One of these two are going to have to do a quick transform so that they're talking about the same parameter. So let's take experimenter 2 and let's transform his posterior into a posterior on mu. However, before we do that, one question you might want to be asking yourself is, at this point in the likelihood where we just plugged in 1 over psi, do we need a Jacobian? So do we need a Jacobian to do this simple insert for the likelihood? It might be a midterm question. It's a good question to ask yourself. Then the next question is, when we transform the distribution on psi, do we need a Jacobian? And I'm going to answer that one for you. You absolutely do need a Jacobian when you're doing the transform on the posterior side. You don't need to do it on the likelihood because the likelihood is a probability distribution over the data space. But once we bring in this prior and we create our posterior, now we're in a probability density in our parameter space. And so when we transform, we have to add that Jacobian to manipulate the space and make sure we're all in the same playing field. So let's do this transform. So we want mu with our data, sigma squared. It's going to be proportional to pi psi, where we're going to plug in 1 over mu, let me write that real quick, psi equal to 1 over mu, conditioned on our data, sigma squared. So it's just plugging in our variable, now times our Jacobian term, which would be 1 over mu d mu. Okay? This doesn't make sense? Hit up review session, hit up office hours. We gotta get you guys to understand transforms, or else it might be a struggle for on the midterm. Okay? So let's just plug and chug away here. And this will be proportional to e 1/2 minus x bar. I'm gonna just plug that in. And we're gonna get mu. 1 over whenever mu is just mu squared. Sigma squared over n. But we can't forget about this Jacobian term, and so, which is 1 over mu squared. Here's the thing you should notice. When experimenter 2 transforms their data from the psi space to the mu space, this equation here does not match experimenter 1's. And so, when these two, if they were to keep this non-invariant to transforms prior, they're not talking about the same probability density on mu. Thing though, is if we had a lot of data, and we got more and more data, asymptotically, they would start to match. And here's a little picture to help understand why. It's all about that likelihood. So if n is small, our likelihood will pretend that's a good likelihood. Will kind of look like that. If n is big or large, I'm going to change markers again. If n is large, our likelihood is going to start looking very peaky. Sorry for the color change, that's our likelihood, that's our likelihood. Now if we had our flat prior on everything, black marker, kind of going like that. As n's going to get bigger and bigger, our likelihood is going to get peakier and peakier, so our flat priors aren't going to have as much impact on that posterior. However, practically, do we ever see so much data that our likelihood becomes super, super peaked? Different cases, different subjects, a little bit of variation there. But key point is that under this non-invariant to transforms rule, these two experimenters don't match. Fact, this also shows that a flat prior is not invariant to transforms. Okay? So while this seems appealing, and it's like, yes, flat prior, we don't want to do it because our inferences and our discussion of these two experimenters want to be the same. So let's come up with a rule that would be invariant to transforms. Also notice, real quick, and this is why experimenter 2 is off by that Jacobian term. And so, by having this prior over here look just like the Jacobian term almost, that's why we want to use the second choice. But I know this guy, and he made a rule. Erase this. He said, here's another rule. And I'm going to tell you it will be invariant to what? Two transforms. Okay? And this rule is, I'm going to tell you already, this is going to be Jeffrey's rule. And what I'm going to do, or this is going to be Jeffrey's prior, sorry, not rule, prior. And what I'm going to do for this class and the next class is I'm going to leave this little j up here, just so that we know it's Jeffrey's prior. Proportional to expectation x d theta log likelihood of theta squared expectation 1/2. Let me do one thing real quick. Boom. Okay? Let me just take a step back. Always helpful to take a step back and look at this, make sure all my notations are right. Yes, okay. Brackets sometimes, they get you. So right here, I want you guys to take a quick second, pause the video if you have to, and tell me and think about what this, let me color it in blue. Right here is. Take a second. Okay? This quantity right here is known as Fisher's information. Typically, a lot of times, it's also denoted by I and then theta, because that is the parameter we're denoting right now. Okay? Fisher's information, for those of you that took Stat 5114, probability to inference, will know that Fisher's information comes back into the Kramer-Rao lower bound, where it's actually the inverse of the Fisher information. And it gives us a good way to bound the variance of an estimator and understand how that acts. We're using it slightly different. We're using it to help us develop a prior. Okay? Now, I haven't really talked to you guys about how Jeffrey kind of came up with this or the understanding it. I'm kind of just giving it to you guys so that we can use some examples, understand some of the priors we've been using, and then next class we can talk about and derive this and why it makes sense. So stay tuned to next class. The other cool part is sometimes taking the derivative and then squaring it can be a little bit complicated. So, if a certain property, which is Fubini's, holds, then this statement up here is equivalent to expectation x d second derivative log likelihood theta, given our data. Boom. One half. Let me take a quick look at this. Forgot something. This is key because this could mess you up on an exam. I've seen it happen to a couple students. For this, you need a minus sign. How can that help us remember? In this formula, everything is squared, which means that this quantity is going to be positive. The expectation of a positive quantity, still positive. The square root of a positive quantity, still positive. So we know that this is positive, and if you worked this out if you worked out this chunk without this minus sign, you'd see it's negative. And so that will be a good reminder of, hey, this needs to be positive, that's why we need that negative sign. I've made the mistake, I've seen a lot of people make this. Don't forget your minus signs. It's going to save you some time in the long run. So Jeffries came up with this invariant to transforms rule. Let's see how it works in the context of a couple of examples, okay? This is really hard to erase. So our first example that I want to show you guys is, just remembering my examples. Example 1. We're going to say our data, so x is going to come from a normal mu sigma squared, and for ease of notation, I'm going to just call it sigma squared v right now. Okay, it's just going to be a little bit simpler to see it v rather than sigma squared. I am using only one data point, but to show our concept, we're going to be taking the expectation at x, so we're going to be averaging out x anyway. If you want, you can also do this problem where you have, only black markers are coming out of the back pocket right now. You can look at this problem, xi follows a normal mu sigma squared, which equals to v. And I'll briefly talk about that if we have more data points, but it's all just going to come into that likelihood. So let's look at this. Our Jeffries prior for v is going to be proportional, we'll use our green brackets, to the expectation. We're going to use this one down here because it's easier in this case. Expectation with respect to x, d squared d v log of 1 over v e to the minus x bar, we're going to say x, minus mu squared 2v. As a side, because I know someone asked me about it during class, if we were working with the xi's, all that would change is this would be x bar, and this would be v over n. Things will start canceling out anyway, and they'll look the exact same as what we're going to do here. So whether I have a lot of data or I can just use 1 point right now, because we're going to be averaging out. So let's just do some math real quick. This one, I'll take it nice and slow, make sure we're getting all the steps, and then the next two examples, I'll go a little bit quicker and skip a couple steps. So expectation of x, taking the derivative, second derivative, but let's take that log. 1 minus 1/2 log v minus x minus mu squared 2v. Let's make sure we get our parentheses all right. 1/2. Okay, proportional to expectation x. You're going to take the first derivative. Let you guys take a look at that real quick. Just take a second. Okay? Going to take the first derivative. So we got to remember to keep this. 1, 2b minus. This would be okay. I'm trying to do my math. Yes, chamber. Okay, so we just took that first derivative. Now we're going to take the next derivative. That's minus, that's a plus. One half. Okay? Proportional to, now we're going to take the expectation across this. Our expectation is respect to x, so x is the random variable, and v and mu are known. So this expectation is going to slide across and just end up in the numerator of this fraction. So we're going to have minus, don't forget that minus sign, it's easy to drop. That is squared over. Minus expectation of x minus mu squared v3 bracket 1/2. Okay? Now, I want you to take 1 second and think about what the expectation of x minus mu squared is. Take a second. It will be, the expectation of x minus mu squared is v. So note, is v. It's the variance. So this just breaks down into minus 2v squared plus v over v3. All to the one half. Here's the thing. Take a quick detour. If we were still using the xi, again, we would have x bar we would also have this variant, we'd have the ends floating in, and so things would start canceling out and you would get the same thing, okay? So if you don't believe me, test it out, and you'll see that we would get the same thing because those ends and all that will cancel out. Now let's just finish this problem and see that the Jeffreys prior on V is going to be proportional to 1 over 2V squared to the half power. To the half power, which means it's proportional to 1 over V. Okay, so let's write that down, and then we're going to go through a little bit more math. So for example 1, when our x's came from a normal mu, again, mu is known for simplicity, sigma squared is equal to V, we found the Jeffreys prior for V equal to 1 over V. Not equal, proportional to 1 over V. And this should look familiar because in our inferences thus far, when we were creating our posteriors for sigma squared, it was 1 over sigma squared because V and sigma squared are equal. Now, Dr. Lehman really likes using the precision because he knows the conjugate of the precision is a gamma. So let's say, instead of using variance, instead we were curious about what is the Jeffreys prior for precision. I'm going to go through the math a little bit faster on this one. It will also be good practice for you guys to try it out. So instead, we are now curious about precision. And what is the Jeffreys prior for phi, proportional to? It's going to be minus expectation x. We're going to take two derivatives with respect to phi log of phi 1/2 e to the minus x minus mu squared 2, and there, phi needs to be up here, minus, boom, boom, 1/2. Okay, still following this rule, using the likelihood, we're going to take the second derivative and go across that way. Okay, so I'm going to log it and take the first derivative all in this step, just so you're aware of what I'm doing. D phi would be 1 over 2 phi minus x minus mu squared divided by 2. So I took the log, which would be 1/2 log of phi. Taking the log of phi, it's going to drop on the bottom, you still have that 1/2. Then I'm going to take the log of this, and you're going to be left with this upper quantity. Taking the derivative with respect to phi, we're left with that. Now we're going to take our second derivative. So, just taking derivatives. Now we're going to take expectation with respect to x, there's no x in here, so it is just that quantity. Multiply it by 1, and then we're going to square root it. So we're going to do a lot of steps in one. Phi is going to be proportional to 1 over 2 phi squared, 1/2, which is proportional to 1 over phi. So, this is example 2. Apologize for that. Example 2. Example 2, we're just going to look at these real quick. We were curious about x's that followed a normal, and we were interested in the precision. 1, okay? Up. Yes. We were curious about the precision, and we found that these markers die out fast. The Jeffreys for phi is proportional to 1 over phi. Okay? Now we've seen these two priors, we've used them. Now we have some reasoning. If someone goes, why did you choose that prior? You can go, well, they're Jeffreys priors, they're invariant. They are invariant to transforms, and I like that property. And so now we have good, at least a reason on why we are choosing this. The key point though, is that under two different parameterizations, me, who I like using variance, and Dr. Lehman, who likes using precision, if we used these priors, when we talk about that posterior, whether it's on phi or the variance, we'll be talking about the same distribution, and that's important. And if you don't believe me that these two priors, 1 over v and 1 over phi, are the same, let me convince you. So, how we're going to verify? That the Jeffreys on the variance contains the same info as the prior on phi. If we were to do prior on phi through transform, so just doing transforms, our prior on v is 1 over v. Or, actually, no, that's an equal sign. So equals 1 over 1 phi. We also know that this is going to be 1 over phi squared, and thus 1 over phi. Same information. Okay? Now the last thing I want to say to you guys before this video wraps up is thus far we've kind of understood why we want to use these two priors for our scale. Question is I want to now validate to you guys why we use the flat prior for mu. And it's all through Jeffreys again. One thing to also note is that this is the conjugate prior. We know the conjugate prior for precision is through a gamma, and this would be a gamma 0, 0. So knowing your distributions and understanding which parameters invoke different things, also very important. So last example, and a pretty quick one, is we've done the Jeffreys prior for our variance and for our precision, verified that Jeffreys priors is going to give us. If we use Jeffreys priors, we're going to be talking about the same distribution. Now, I want us to ask ourselves, what is the Jeffreys prior for mu? So pi j mu, it's going to be proportional to expectation of x, derivative respect to mu, our log likelihood. Again, we're on mu, and our sigma or precision, whichever one you're looking at, is fixed. So it would be e to the x minus mu squared to sigma squared, or we're using v. I want to keep it consistent for you guys. V, boom, 1/2. So if you can, pause the video, take a second, try and derive this real quick. Okay? Hopefully, you guys saw that a marker will work eventually, you guys. When you take the log, you're going to be left with this. Then you're going to do the chain rule, and you're going to see you'll get x minus mu to v. Oop, forgot one thing. There we go. D mu. After the first derivative, you'll get positive 2x minus mu over 2v. Now if we take the derivative again, we're going to be left with minus the expectation respect to x, key to remember, minus 1 over v, all to the 1/2 power. Now, when we take the expectation respect to x, there's no x, so we're just going to have 1 over v. We're going to multiply that by 1, and then 1/2 power. So 1 over v, half power. Here's the thing to remember. Our prior is on mu. This has nothing to do with mu, and our v is constant. So this is proportional to a constant. Typically, we choose 1 because 1 is simple and easy to multiply by 1. So this is typically chosen to be 1. Okay? So in today's class, what we did was we tried to motivate why Jeffreys prior, or to be invariant to transform, is important. It's important so that regardless of the choice of parameterization, when we start to talk about our inferences and our parameters and the distribution on them, we're talking about the same thing. There isn't some other space that we are. We're talking about the same thing. We also talked about a non-invariant transform, which was the flat or uniform prior. And you don't want to do that. If I can make any point today, don't do that prior, okay? Next lecture, we're going to motivate this and kind of understand where this is coming from. And then Dr. Lehman's going to take over and talk about Wisharts so we can start learning about distributions on matrices. Thank you guys. I'll see you Wednesday. Have a great day.